Okay, so we're now going to cover the second part of section 5, which will deal with some more theorems that have to do with continuity, as well as a couple of important theorems that we'll use quite a bit in this class. And so this section or this part is fairly important. So let's start off with our first theorem. And this first theorem basically has to do with composite functions. So we could say if f is continuous at b and the limit as x approaches a of g of x equals to b, then we can say that the limit as x approaches a of f of g of x is just the same thing as f of b. So what you notice here is, of course, it's kind of like we are using direct substitution. Because look at what's happening here. If the limit as x approaches a of g of x exists, and it is b, then we're practically, what we're doing is this limit part, we're just plugging in b into f. Now what's important is we also need to make sure that whatever this limit is, if it exists, since right now we're calling it b, we need to make sure that f itself is continuous at b. So if it's not continuous at b, then we have to be careful. We can't use the direct substitution. So we have to kind of take different approaches and say, look, this limit still may exist or it may not, but we get a lot of nice results if f is continuous at b. So if this limit exists and it is b, and at this value, if f is continuous, I could just simply just plug in b into the function and get the answer. So in other words, here's what's another way of expressing this. So that is the limit as x approaches a of f of g of x is equivalent to the f of the limit as x approaches a of g of x. So these two mean the same thing. So what are we saying? You could take this limit inside the composite function only if f is continuous at the output of, or whatever this limit is. So whatever this limit goes to, if f is continuous there, then I can move this limit inside, evaluate this, and do a direct substitution. Okay, so let's look at our first example, and we'll put this theorem to use. We could say evaluate the limit as x approaches pi of the function sine of x plus sine of x using continuity. So if we look at this, here's what you're going to notice. You're going to say, now look, this is a composite function if you look at it, because it's kind of like we have sine of x, and inside of sine of x we have another function which is x plus sine of x. So here's the good news. Since sine, if you think about the graph of sine is never ever discontinuous. In fact, the graph of sine, if you remember, looks like this, and so it's always continuous. It'll never have discontinuities. So since sine is continuous, what we could do is we could say, look, limit as x approaches pi of sine of x plus sine of x. Since sine is continuous everywhere, no matter what this spits out, this will never be undefined. So I could move the limit inside. So this equals to the sine of the limit as x approaches pi of x plus sine of x. Now remember, this limit is only concerned about x values. So notice how the x values appear inside of this sine function. So now here what I could do is x is continuous everywhere, right? If you remember, we had a theorem that said x is continuous everywhere, sine of x is continuous everywhere. So we can just plug in or use direct substitution. So what does this become? It becomes sine of pi plus sine of pi. And now we could simplify this. Sine of pi, that's 0. So we get sine of pi plus 0. And pi plus 0 is still pi. And then we get another sine of pi, which ends up being 0. Okay? So let's move on to our next theorem, which has to do with some more concepts of continuity. So our next theorem says, if G is continuous at A and F is continuous at G of A. Now, why do I care about G of A? Well, this is going to have to do with a composite function, and you'll see exactly why I care about G of A in a minute. So then, the composite function f of G given by f of G of x, which is the same thing as f of G of x written as that, this is also continuous at A. So basically what we're saying is we can use direct substitution right away as long as this composite is continuous. So here's what we're saying. Look, if G is continuous at A, what does that mean? Then I could, to find the limit, I could just plug in A into G, which gives me an output of G of A. But then the question is, what happens to F at G of A? Because remember, to get to F, I first need to go through G first. So then if F is continuous at whatever G spits out, which right now is G of A, then we know for a fact that F of G of X is in fact continuous at A. So here, if G is continuous at A, F is continuous at G of A, then F of G of A, that whole composite is continuous at A. Okay, so for example number 2, we'll just use example 1. We could say, look, notice from example 1, we could treat example 1 as a composite function as we talked about. So I could say if we let f of x equal to sine x, or x plus sine x, if we let f of x equal to x plus sine x, and g of x equal to sine of x, then what do we have? We have g of f of x is what? Sine of x plus sine x. Okay, so here's what we could say. We could say, look, since, so let's continue this, since f of x equals to x plus sine of x is continuous on all reals, okay? We could also say that g of x equals sine x is continuous on all reals. What does this imply? This implies that g of f of x is continuous on all reals. Okay, now one thing I want to point out here is for this one, I wasn't too descriptive as to why it's continuous on all reals. We're actually going to use the theorems from the first part. See, here's what we could say. Since y equals x is a linear function, what do we know? Linear functions are continuous on their domain, which is all reals. And then if you look at sine of x, that's a trig function, which also the theorem said if you have a trig function, that's also continuous on its domain, which the domain of this guy is on all reals. And then we had another theorem that said, look, if this is continuous on all reals and this is continuous on all reals, then their sum is also continuous on all reals. So for this one, I should have been a little more descriptive. but since I was kind of limited with space, I kind of just said this is continuous on all reals. But we will do an example shortly where I'll kind of break this up into pieces. But once again, notice I'm not mentioning any theorem numbers or anything of that sort. The only theorems that will relate by name or will specifically talk about are the ones that have names, okay? So in fact, the next theorem is actually an important one, which has a name. So this is actually known as the intermediate value theorem. So let's first talk about what the intermediate value theorem says, and then we will kind of I'll visually explain to you exactly what it's saying, and then we'll do an example. But it's very important when you're using the intermediate value theorem or any theorem that you're using, you need to make sure that the hypotheses are satisfied. If you don't satisfy the hypothesis, then you cannot use the intermediate value theorem whatsoever. Okay, so let's just say, here's how it starts off. Suppose that f is continuous on the closed interval from A to B. Okay, now let's be careful here. Let's pay close attention to this. This is very, very important. So we're saying f has to be continuous on the closed interval A to B. Okay, so the semantics or the language here is very, very important. If I don't have a closed interval, if I have, let's say I just say it's continuous on an open interval, that's going to be a big problem. And I'll show you what would happen is if we ignore the fact that it has to be a closed interval. So remember, if you're using the intermediate value theorem, the first thing you need to make sure is you check continuity on the closed interval, or you show it's continuous on the closed interval. So then, and we could also say, and let n be any number between f of A and f of B. So what we're saying is capital N is some number between f of A and f of B, okay? And of course, we also need to make sure where f of A does not equal to f of B. So basically, the y value at A is different than the y value at B. So this is basically my hypothesis of the intermediate value theorem. So I haven't yet stated the conclusion, but before we finish off this theorem, let me tell you what's important, or what are the things you need to show before you could use the intermediate value theorem. First step, you need to show that f is continuous on a closed interval. Whatever your interval may be, it needs to be continuous on the closed interval, not open, okay? And then what you do is you check the y value at A and the y value at B. And then you need to make sure that the y values of A and B are not the same, okay? So, and what do we know? And this capital N is going to be any number between f of A and f of B, okay? So then what we could say is, then there exists, remember this reverse or the backwards E means there exists. So then there exists a number C in the open interval. So basically, remember, this means it's inside. So then there exists a number C in the open interval from A to B such that f of C equals to capital N. So in other words, here's what we're saying. If this function is continuous on the closed interval from A to B, and N is the number between f of A and f of B, then somewhere in this interval from A to B, there's a number that we're calling C, where the y value of C is the same thing as N. So basically, the whole purpose of this intermediate value theorem is to show us that some y value exists for this function. So visually speaking, here's what happens. Let's pretend that this is A and this is B. And I have a function that's continuous from A to B. And I drew this like this on purpose. Because the intermediate value theorem, now let's be careful, when we say there exists a number c, there could be more than one outcome. But let's pretend that this is n, which notice what happens here. N, so this is actually f of a, and this is f of b. Now clearly you could see that n is between f of a and f of b. So look, since this function is continuous on the closed interval from a to b, and f of a is not equal to f of b, and n is somewhere between f of a and f of b, notice how there's somewhere inside this interval, which is open, not including the n's, there's somewhere, at least one place, where the x value will give me an output of f of n, or of n, not f of n. And what you notice is, in fact, there's more than one place. If you look at it, the first place is c. So notice how if I plug in c into this function, this is the graph of f of x, f of c is going to give me n. So that's what they mean that there is a number c. Now, there's, in fact, more than one. We can call this also c, right? If I plug in this x value into my function, it'll also take me to n. And lastly, there's also another one here, right, where if I plug this in. But what we care about is, does there exist at least one? So as long as the whole purpose of the intermediate value theorem is there, it tells you that there's at least one place. You're guaranteed to have at least one place where if you plug that x value into the function, you'll get that y value that we're calling n. Okay, so what's the purpose of this? For the most part, one of the biggest applications to the intermediate value theorem is to show that a function has a root. Because what we'll notice is we can't always find x-intercepts of a function by hand. Sometimes we're going to run into some problems. So the intermediate value theorem shows that a root exists. Now, keep in mind that the intermediate value theorem itself does not find you the root. It just shows you that a root or something exists, okay? So for the third example, which this is just continuing the number of examples we did from earlier on. So what we could say is that show that there exists a root of the cube root of x equals to 1 minus x on the interval from 0 to 1. Okay, now here's the problem. If you try to use your skills from math analysis to find the x-intercept of this guy, you're going to have some difficulty. It's not as straightforward, okay? So we won't be able to find the x-intercepts of this guy or the roots of this guy by hand. We would have to use a graphing calculator. However, what's the purpose of this example? Is it asking us to find the roots, or is it asking us to show that there exists a root? And the answer to that is they're saying, tell me that a root exists. They're saying, I don't care what the root is, just tell me that somewhere between x equals 0 and x equals 1, this guy has an x-intercept. That's all it's saying. So here's where the intermediate value theorem comes into play, and it's very, very important. So here's what the solution is. So we're going to using the IVT. So the IVT is just short for intermediate value theorem. So from now on, whenever you use the intermediate value theorem, you can just say IVT, and we'll all understand what you're saying. So what's the first thing we want to do? Well, before I do anything, I'm just going to write this as we have cube root of x equals to 1 minus x, which implies this is the same thing as x plus cube root of x minus 1 equals to 0. So all I did is I took this guy to the other side, and I set this guy equal to 0. Now, why am I doing that? Well, we're trying to find a root here, aren't we? So if you think about it, this is my function. That's f of x. So I want to show that f of x takes on a y value of 0. Okay? So if I'm going to use the IVT, what's the first step I need to show? The first thing I need to show is that this guy is continuous on the closed interval of this guy. So what I'm going to do is I'm going to basically try to show that this guy's continuous on the closed interval. So here's what we could do. We could say, look, if I have, and I'm going to rewrite this in a minute, just to, so I'm going to rewrite that as this, just to make it easier for you to see as to what's going on. Okay, so I just kind of swapped these two. So here's what I could say. Let's start by talking about continuity. So the first thing we need to do is we need to mention that this guy's continuous on the closed interval from 0 to 1. So I'm going to break this up into pieces. I'm going to say since cube root of x is a root function, we know it is continuous on its domain, which is what? Which is from negative infinity to infinity. Which, of course, look, if the cube root of x is continuous from negative infinity to infinity, what does that imply? It implies it's also continuous on the closed interval from 0 to 1. Of course, 0 to 1 is contained in there. So if this guy's continuous on all reals, it's also continuous on the closed interval from 0 to 1. Now, we could also say, since, and by the way, this part right here, I just used that theorem that said, look, root functions are continuous on their domain. So notice how, since the theorem doesn't have a name, I'm not using its name. I'm just pretty much writing it out, and I think it's clear to us that I'm using that theorem. So also we could say, since x minus 1 is a linear function, it is continuous on its domain, which is from negative infinity to infinity, which implies it's continuous on the closed interval from 0 to 1. Okay, now here comes the second part of the theorem. If you remember, we had a theorem that said, look, if f is continuous at a and g is continuous at a, then their sum is also continuous at a. So look at what's happening here. If cube root of x is continuous on the closed interval from 0 to 1, and x minus 1 is continuous on the closed interval from 0 to 1, then cube root of x plus x minus 1 is continuous on the closed interval from 0 to 1. So we could say this implies that the cube root of x plus x minus 1 is continuous on the closed interval from 0 to 1. And so this is actually the other theorem that we had from this section in part 1, 2.5 part 1 that we did. So if you look at this, just this notation here or this writing here is we're just using those theorems without really stating them because they don't have a name. Okay, but it's clear to us that we're using the theorem. Okay, so what have I done so far? So far what I've done is I've shown that this function here is continuous on the closed interval. Okay, so that's the hard part. Now comes the easy part, which means we plug in 0 and 1 into the function. So we could say, notice that f of 0 equals to the cube root of 0 plus 0 minus 1, which that equals to negative 1. Okay, and f of 1, which equals to cube root of 1 plus 1 minus 1, which that equals to 1. So what do I notice here? When x was 0, my y value was negative 1. When x was 1, my y value is 1. So what did you notice? When I went from 0 to 1, when my x value changed from 0 to 1, my y value changed from negative 1 to 1. So what does that mean? If it changed from negative to positive, that means it must have crossed the x-axis somewhere between 0 and 1, which means I have a root somewhere between 0 and 1. So you see why it's important, or how could I be so certain that this crosses the x-axis? Well, because we just showed it's continuous from 0 to 1. So it's not going to have any breaks or cuts. So for example, if I were to argue and say, well, how do you know it crosses the x-axis from when I go from x equals 0 to 1? How do you know it doesn't look like this, where it does this, and then all of a sudden it has a jump discontinuity, and it does this, which notice how this doesn't have an x-intercept? Well, then your whole point is going to be, why do we waste our time showing that this guy's continuous from 0 to 1? So in other words, what does that mean? When x is 0, we're at y is -1. When x is 1, y is 1. From here to here, I'm supposed to be connected all the way through. So if you're connected all the way through, somewhere between 0 and 1, you have an x-intercept. So that's the importance of continuity. I hope you guys are understanding why it's important to show it's continuous, because if you don't show continuity, then you can't do this step. You can't say that, because what if we have a jump discontinuity like I drew up earlier? Okay, so here's what we could say. We can say, thus, by the IVT, so here's where I'm giving credit to the intermediate value theorem, because notice how all of this is the hypothesis of the intermediate value theorem. So now we could conclude by the intermediate value theorem. We could say there exists a number C in the open interval from 0 to 1 such that f of C equals to 0. And so notice how we're not finding what this number is, but all we did is we just showed that somewhere between 0 and 1, there's an x value where when I plug that x value into my function, the y value will be 0. And that's basically what a root is, right? Or an x-intercept. So that pretty much takes care of what we did here. Okay, so before I wrap this up, there's one other thing I want to point out to you. And this is a question I want you to think about. And we can talk about this in class and see what you guys think. My question to you is, if f of x is continuous on the open interval from a to b, and f of a is less than 0, which means f of a is negative, and f of b is greater than 0, then that means f of b is positive, then there exists a number C in the open interval from a to b such that f of c equals to 0. So now my question to you is, true or false? Okay, and explain to me how this is true. Or if it's false, explain to me how it's false, or give me a counterexample. So all I'm saying is f is a continuous function on the open interval from a to b, and f of a, when I plug in a into my function, I get a negative number, and when I plug in b into my function, I get a positive number. So since this changes from negative to positive, does that mean that we're guaranteed to have some x value between a and b, where if I plug in c into the function, that equals to 0? So think about this question. This is actually a good question. And then we'll also talk about it in class, okay? So that basically takes care of the second half of section 5. So that's basically it.